Okay, so for PC18, that's this next problem. It asks about the graph parameterization to find a formula for the curvature of a graph. Now, critically notice that what we have here, we were not given this curve as being the graph of anything. What we were given was that position was a function of time, and that's where we could take derivatives with respect to time on all of these things. So this was we were given a parametric curve, right? And now the problem says, well, suppose we have a graph given to us. Suppose we're looking at some graph. So here we have y equals f of x. That is not a parameterization as given, so the formula that we've derived for curvature doesn't apply. Right? So let's figure out how to come up with a formula for curvature that will apply to this situation. And the graph parameterization is the key here. The hint says use the graph parameterization. So specifically then, we're going to parameterize that curve by choosing to let x equal to t, let y equal to, well, y is f of x, x is t, so y is f of t, and that gives me my parameterization, t, f of t. There's my graph parameterization. That's x. That's y, functions of t. And now I can just plug in to the formula that I have for curvature, which is just the absolute value. And I got to plug in all this stuff here. So x prime, y double prime, and all that. Now, good news, x prime, easy to calculate. It's 1. Y double prime, well, okay, the second derivative of y with respect to t, that's just f double prime. Now we have minus, let's see, now x double prime, well, that's 0, it's lovely, times I don't care, because I'm multiplying it by 0, and then we divide by, well, let's see here, we've got something to the 3 halves here, but what are these things? Well, I have x prime squared, well, x prime is 1, so x prime squared is just 1, and then plus, let's see here, y prime squared. Well, y prime is f prime. So altogether, what I have is absolute value of f double prime divided by 1 plus f prime squared quantity to the 3 halves. And there's your formula for curvature of a graph of a function. Yeah.
Sorry. Returning to the previous problem, I understand why there's no absolute value on the denominator, but why are there absolute values on the numerator and the left side of the equation?
On the previous problem?
Yeah.
Yeah, sure.
On what you had at the end there.
Why is there absolute values here?
Yeah.
Yeah. So the reason there's absolute values here is because we're defining curvature to be the absolute value of d phi ds. And we computed I forgot that. We computed d phi ds here, right? That came from d phi dt that we had computed from way back. But we had to take the absolute values. That's just the definition of curvature. And the idea there is that if something's curving that way or if it's curving that way, well, the curve is curving the same amount. It's just in different directions. And that sign only points to which direction is it curving. And so for this instance, we want curvature to be an intrinsically positive thing. Okay. And let the record show, by the way, this is not always the case. I mean, if you take a course in differential geometry, they're going to define curvature in a different way, and it is not intrinsically positive. You keep the minus sign on there to tell you something about the way that it's curving. Depending on what type of curvature you're talking, there's lots of different types of curvature in differential geometry. But for Math 103, for this context, we just want to know the scalar quantity. I mean, how much is it curving? And so we take the absolute value. Thanks. Yep. Okay, let me stop this recording.